Whether in high-performance servers, new energy heavy-duty trucks, or 24/7 energy storage systems, heat generation from core components is an unavoidable physical challenge. As purely passive heat exchange components, liquid cooling plates play a critical role in safely operating the system by efficiently transferring heat away. For prismatic cells, choosing the liquid cooling plate layout is never a random decision. Instead, it requires careful consideration of three core elements: the internal space of the battery pack, heat source distribution, and the target temperature difference along with cooling demands. In this issue, we will first focus on the primary physical constraint that dictates the hardware layout: the pack's internal space. The available structural space inside the battery pack directly determines the first line of defense for heat exchange. If there is enough space at the bottom of the cells, a bottom cold plate is the most common and relatively mature solution. It features a simple structure, low integration difficulty, and a clear assembly path for modules, making mass production much easier. This is similar to the practice at a seafood market stall. The owner spreads a layer of ice on a flat counter and lays the fish directly on top. It uses the large area direct contact at the bottom to quickly absorb the heat from the fish, which is simple and efficient. However, not all systems have ample bottom space. If the battery pack height is limited, or if there is available side clearance between the cells, engineers can consider a side cooling solution. This layout is just like chilling wine or cans in an ice bucket. Because the bottom contact area is small, or there is no space for ice at the bottom, we choose to tightly stack ice cubes around the sides of the bottle. This allows the cold source to exchange heat through the large sidewalls, perfectly adapting to this narrow space constraint. It is worth noting that evaluating the internal space must never ignore the strict limit of pressure capacity. Before finalizing any of the layouts mentioned above, in addition to evaluating the available space and assembly paths, the system's weight limits and the structural strength of the cold plate must be strictly considered. For example, in projects with strict weight restrictions, if the plate thickness is reduced for extreme weight savings within a confined space, such as combining a 0.8 mm top plate with a 1 mm bottom plate for a total thickness of 1.8 mm, local areas are highly prone to fatal bulging deformation risks under an actual working water pressure of about 2.5 bars. This deformation will directly destroy the tight fit of the heat dissipation interface. Therefore, the cold plate layout and plate thickness design must be considered together. A single metric must never be optimized in isolation.
The internal space defines the physical boundaries where the cold plate can be placed. However, although prismatic cells have a regular shape, their internal heat is not released evenly across all surfaces. If our cold plate is placed in the right physical location but misses the main path of heat generation, it still cannot solve the problem of localized thermal runaway. In the next installment, we will deeply analyze the second core element of selection, heat source distribution. We will explore how to build the most direct and efficient heat transfer channels for different cells based on their internal heating characteristics.